And anyhow, thank you very much for the amazing organization and giving me the opportunity to talk here. And today my topic is rewarding the bulk. This is based on the work with Jake Bilton. And also there are related work with Nadav Drucker and Peter Kravchuk, and also the with Baston, Miguel, and Feline, that paper. And also I want to, based on Nadav's talk on Tuesday, rewarding the defects. So my talk will start from the second equation from my first paper, which is the word identity for the tilde operator and the J current. So sometimes I would like to write it in a different way as an integration. So now my W here is a defect. It's p-dimensional. And I can equivalently write it in this way. So because I really focus on the integral identities, so this is the charge. So it's a slightly different. I can write this one as some integration of the one above. And to distinguish the bulk operator and the defect operator, as the name shows, here I will use this hat as the symbol for the defect operator. So if I want to draw a picture of this formula, I would say now I have a p-dimensional defect, which is W, and I have my current J acting on this defect, and it shows that this action will give me the integration over the line. So the question arises, like, what if I act on with some current J twice on this defect? Still, I would like to show it in a picture.
I'm still confused. When do you mean current and when do you mean the charge? We're using the same symbol.
I'm somehow mixing the abuse the use. So let me say the charge. I really want to use the charge. Yes, I'm considering a Euclidean defect, but it doesn't really matter if I want to use the Euclidean signature or Lorentzian signature. Okay. But yes, now I'm considering a Euclidean defect. The normal direction? Mm-hmm. Yes, sure. I somehow like let this charge among the whole space because it's like most of the space except for this defect is vacuum, so it acts on the vacuum for nothing, and only when it acts on the defect it becomes meaningful.
Because usually when I construct the charge, I take the time component of the current and I integrate that with the space one. This is not
think it has to be contracted with the normal.
Yeah, but then you integrate it with the T.
The T is the. So it should be
No,
straight
no,
up.
no.
No, it's
Should be, yeah,
Yeah. You put it base like.
sorry, I somehow don't really remember the details here.
Take the charge, achieve the defect, or before you send on the defect just surrounding it, or is it piercing
Surrounded.
like a cylinder surrounding it?
Mm.
Of course, you can complain about it. Or you can see
it's a defect.
But let me skip this question for the moment. It's not a very, it's like more like a picture demonstration. I didn't really mean this very rigorously. So if I have two charges acting on the defect, I will naively expect it gives me, let's say, double integration. But at the moment, if I write it in this way, it's kind of confusing because I know that the order if I firstly act on J1 and then J2 will be different from what if I first act J2 then J1. What I mean is like they are different because normally we know that J1 do not commute with J2, but this thing do not show when I write the integration in this way. So the issue is that there are some contact terms when my J2 approaches this J1. So as Nadav said in his talk, I can, if I write the tilt operator endpoint function, I will do it as separate endpoints, and also some contact terms when T1 approaches T2, and even the more singular terms. So that's the, I will use another blackboard because now I want to go to the case with the bulk operators. So let's say now in my theory, I have not only the defect, but also a bulk operator, not one. Let me draw two. And I again want some charge acting on the whole system. So it will separate into two paths. One is that this current acting on a bulk operator and the second part is the same as the defect case. where it's acting on the defect, and give me the same integration on the tilde operator. So here I want to emphasize that I do not consider any bulk anomalies. Maybe I should have done it. I really should have done it, but I don't consider that case at the moment. So as this picture shows, because the action of the charge on some bulk operator is pretty well studied, and on the defect operator is the same as what it is in the dev's talk. So it's very straightforward to apply the same formalism here. And so if I want to consider like double charge acting on this system, like what I did in the pure defect case, again, the contact terms will be important. It will be basically the same, but now with the bulk operator. So yeah. Electrodynamic, what would be TI?
Is it TI head or TI? Is there a difference? I think it's same. Head means a hug. No, in the delusions, it's TI head.
What is the defect you are considering? Because it's like as somehow this identity shows, you only have this TI once there is some symmetry breaking. So this A is broken to.
So the J here is a current for global symmetry, not like.
So it's not gauge.
So it's not a gauge symmetry, and it's not an electric current.
So TI is like a source, or what is it? Is the displacement operator TI?
I would say TI is really a operator.
Maybe you can explain what the tilde is.
Yeah. So for the tilde operator, maybe let me show it in the own model, something. So let's say in own model, I have n scalar phi I from 1 to n. And now my defect is like a magnetic line. I have some coupling H and.
Can you again write bigger or?
Yeah, sorry. So here is tau n, and my tilde operator is really like, so this defect breaks the ON symmetry to ON minus I because here I choose one scalar among these n scalars. And my tilde operator is well, and I somehow need to normalize it correctly, but it's infinitesimal, so it's okay. So this actually is identical to this phi n here. And if I expand it in terms of epsilon, this would be the leading order that I have. That's actually what the tilde operator is in that case. So there are some again some separated distribution. And there are some contactor ones. So it's very similar to the pure defect case, just with some bulk operators. Okay, and as I said, this is a very naive picture demonstration. And now let me do something rigorously to get the formulas. So separate. Yeah. So I consider now a system. I didn't really explain what this notations means, but here I say the directions along my defect are tall, and perpendicular to my defect is x perp. And here I use I say that my bulk operator is transforming in some representation of the bulk of the global symmetry group J, and this I is just to represent the representation. So in the pure defect case, I can write like, if you still remember Nadav's talk, so just to remind you, this W is like the couplings of the tilde operators on the defect. So I can write it as T Yes. But because it could varies along the line, so I use a parameter W to represent it. And in the here, A is the anomaly, and Lj means if I use another group element, let's say W, in J, and acting to deform the system, I will have like I will expect that it's identical to the right-hand side before the action. So in some other way, it's actually what I said here. So the right-hand side, let's say, is I have a system, and now I use some group element to acting on this system. It gives me some small definition, but generally, I will expect them to be equal because it doesn't really matter if I choose here to be phi n or phi n minus 1. It's just that in some case, there would be some anomalies. So I use this factor to denote that. And in the bulk case, this can also be generalized for free. That I will have my partition function is a function of the left action acting on the bulk operator, and also the left action acting on my defect. It gives me the same factor because here I don't consider any bulk anomalies. And in the Duff's talk, he shows that one can expand this LJW at linear order in lambda because I say my J is into the lambda, but at any powers of W. And to some to the also the other lambda square. So I somehow want to emphasize again that this is enough because for us lambda is a constant and W could be a function along the line. So if I want to get the behavior of this LJW at order lambda square or at higher orders, I can just turn one of my W to be a constant. Then I get the behavior here. So this is really enough. Let's say it's not an approximation at the leading order of lambda, but it really extracts all the behavior of any orders in lambda. It's just we do this to make the most use of the functions that could be different along the line. So and the LJR is easier. I can do it in the write a similar expression for that. But this row of lambda r is it's linear in lambda and r, and it gives you some matrix on the basis. And this one is like how the generate generator EI, which is a basis of the global symmetry group J, acting on the basis of the representation R. So later on, I will just write it more compactly as Ti uses Ti. So after all of this preparation work is done, we can move forward to the expansions in Ln. But for simplicity, here we will only consider the case with one bulk scalar operator. The reason is that if you increase the number of the bulk operator, the amount of the bulk operators, then the system will become more and more complicated in a very fast way. But the idea just normally apply everywhere. For any number of the bulk operators and defect operators. Okay. So after writing out the all of these complicated formulas, the most simple equation, but non-trivial that I can show is that for n equals to 0, what I will have is Ti alpha beta O beta x0 So in the pure defect case, it will be just the one-point function of T after integration is equal to 0. But with the insertion of the bulk operator, we find that this one is not trivial at all, and it's actually quite useful because you say this is a one-point function of the bulk, which we know is like AO over X to some power. The power is the conformal dimension of this bulk operator. And on this one is the two-point function. This is because I'm considering a scalar So the integration is on the defect operator, which is this tau1 here, and it's not a hard integration, but this can give us a very straightforward identity of the one-point function A and the two-point function BO.
Right, they're equal, but what happened to the
This one is equal to this one. And here by this C, I mean they are connected correlators, but for the one-point function and the two-point function, we are safe because they are anyhow connected. And there is something that I want to emphasize, that this O prime doesn't have to be the same of this O. So let's again look at the Owen model. So if I have a defect, as what I draw somewhere just now. And the bulk operator I say is phi I, and I comes from 1 to n-1. So this system, I will say the one-pound function of phi I, at least at leading order is 0. But let's say what would happen if I have a J I n, the charge, this acting on the system. So I find that its action on the defect operator, bulk operator, will give me a phi n. And now this one-pound function is not 0 anymore. And its action on the defect will give me the integration of the tilde operator I. And here is still phi I. And I also know that this two-pound function phi I t I hat is not 0. So this is by this we actually built a construct an identity between the one-pound function a phi n and the two-pound function b phi I t. So just to emphasize that the bulk operator on the both sides of the equation doesn't have to be equal.
But the bulk operator. I mean, the bulk operator really is the same.
Yes, you can think of yes, except for the tensor structure.
So in the one-point function of phi, there will be a delta in.
Yes.
In the bulk, it transforms into O n. It's an element of O n. So
Yeah.
really the same operator.
Yes. I just say if I want to decompose it into the on minus 1 and in the on minus 1 point of view. So you can do this for arbitrary bulk operator, and this is very analogous to the displacement case, where you somehow have the you can write the delta O is equal to the integration on the displacement operator and the bulk scalar O. This is given in the paper of and Menary. In there another paper, also by Menary and others. This relation is found for the boundaries, not for an arbitrary dimension defect, but it's basically the same identity. Okay, so and here this is the case when I consider one bulk operator and one tilde operator, but this is true for any number of bulk operator and any number of operators. Let me write the expressions explicitly. So I can actually write the identity for arbitrary number of bulk operator at different places, x1, xm, and defect operators doesn't have to be the tilt. It could be arbitrary operator. And related with some t acting on these bulk operators and a sum, of course. The final one I required to be a T tilt operator. So this is analogous to the defect case where you have the some defect operator with one bulk, with one tilt operator. By doing so, you will somehow get the case without this T. And most of the case, this vanishes because, for example, if all of them are the tilt operators, on the left side, if I want this one to be non-vanishing, let's say I have a 4-point function, and here I have a 3-point function, and if they are all tilt operators, then in most of the case, it vanishes. So this is not a very rigorous equation, but I just want to show the similarity. And this is the above equation is a highly non-trivial identity. It's if I just for simplicity, I want to say I have only one bulk operator, and when I have the one bulk operator and two and also like one, here I have one bulk, one defect, and here I have one bulk, two defect operator, and then it the right hand side gives me a function of one cross ratio. And if here I have a one bulk, two defects, and here I have a one bulk, three defects, then I actually write an identity to relate a function of one cross ratio and the integrated function with two cross ratios. And this generally holds in arbitrary, non-perturbatively and in arbitrary theory. So, but this system is somehow complicated. So in our knowledge, we verify the one bulk, three defect identity in our model in this case. And it already have two cross ratios. So let's do something easier before that. I am considering one bulk, one defect, and also the second term gives me one bulk, two defect. So to write it rigorously, I have this. So I would say just in terms of the computational complexity, this is the most as hard as the 4-point function in the defect case, because in the 4-point function, a pure defect, here I say the PTT, I have 1 close ratio, and I integrate it, of course, with a different measure. It gives me the 2-point function of TT, which is somehow analogous to the first term here, which is also a 2-point function. So let's choose our bulk operator as a scalar that I write as u times phi to some power j, and this is a rank j scalar, and I require my u to be a vector in On and is a null vector, so that it guarantees that O transforming the symmetric traceless representation. And my defect operator, because here I have used this u to contract the indices, I will also use some thing that is u hat to contract the indices of my defect operator. And I also say this u hat is a vector in On minus 1. And for simplicity, I also want it to be a null vector. And from now on, I want to focus on the line defect case because it's simpler. But in our paper, we also give the formula for arbitrary p-dimensional defect. So what I have is that this 2-point function now becomes OJ U x dot and here I use this for short. It's really I mean the distance on the perpendicular direction plus the distance among the direction along the line defect. And the 3-point function is given by, here I say this is U1. Plus another channel. Okay. So yes, sorry, I need to explain it. This theta is the direction along the the defect direction. For example, in this phi n case, I mean my theta is somehow like delta in. It indicates how the defect is charged in this On group. And here this u dot theta j minus 2 means like because my bulk operator is a rank j operator in ON. So here it means that I have j minus 2 u to contract with the defect and 1 to contract with the tilt and another one to contract with another tilt. So if I want to draw a Feynman diagram or something like that, f is a function of the cross ratio. It's a general function of the cross ratio. At the moment, I don't know what it is because it depends on which model that you study. So this channel, if I want to draw a Feynman diagram, is somehow like I contract my two. It's not really that one, but just to show how the indices look like. By this, I mean they are integrated along the line, or they are contracted with the line, something like that. And there is another channel that will look like this. That's the correct one. And the other one is the one that I draw just now. So now in its tensor structure is power j u1 dot. And the f2 is another function of the cross ratio chi. This cross ratio is defined as okay, and here what I write is a whole 3-point function. But if you say like when I write out my equations, I really just focus on the connected part. So here, if I want to consider the connected part, I also write a subscript C. And in the case of the one bulk two defect operator, the correlator is not just connected as the one bulk one defect and just one bulk operator case. So they are actually defined in this way. That's the one bulk two defect connected part is equal to the full 3-point function minus the 1-point function of the bulk with 2-point function of the tilts. So if I want to express it in terms of these two channels, it gives me that F1C is equal to F1, but F2C is equal to F2 minus AO CT. CT is a 2-point function of the tilt. And if I want to match the integrated one-point function with the two-point function in these two channels, I will have like and in these two expressions, 1 and 2. It's just that you plug in the, like here is what you do when you, what you do when you plug the the three-point function into this integration. And because I want to write in terms of the cross ratio, and my cross ratio is like this, and it's from 0 to 1. It's not from minus infinity to plus infinity, because the denominator is written by x1 and so on. And after doing the parameter transformation, that's the result that I get. So the J's on the right-hand side is when there is the T, the charge acting on the bulk operator, it will give you this 3 factors J, because my bulk operator is look like this. There is a index J there. So it's natural that there is some prefactor J appearing. The conclusion now is that at the moment I got two expressions from the integral identities. They sound pretty meaningful. But if I have the expression at, let's say, in some perturbative expansion of the correlator, and I just plug it into this calculation, and I do the calculation just in brute force and naively, what I will find is that 1 is satisfied, but 2 is not. So what's the reason for that? The reason is that there is some contact terms that will also contribute into, somebody like to call it order mixing, because for example, if I look at the order lambda to 0 stuff, and F2C is at order lambda 0, and also the two-point function is at the same order, but I will find something at order 1, order lambda to the 1 will join in this calculation. And because like in the numerator, I have order lambda 1, and in the denominator, I also have the thing with the same power. And this gives me back to this the order lambda to the 0. Let me show it explicitly what this is. So in the OPE, because remember F2, I really need to, sorry. So this is with the U times J U1 hat dot U2 hat with this tensor structure, and the F1 is with U dot theta J minus 2 U dot U1 hat U dot U2 hat with this tensor structure. So for F2, I have this U1 hat times U2 hat, which implies that I need to look at the OPE of these two tilt operator because they contract with each other. And in the OPE of the two tilts, I have my the first operator appearing here is of course 1, and let me write it explicitly. And in perturbation theory, the second operator with the lowest conformal dimension will be the phi operator. And all the operators have the higher conformal dimensions. So what is this thing? Let me say in our model, I have this phi n, and that is what my defect is coupling to. So I have already told you that this phi I, when I is going to 1 from n minus 1, they are the tilt operators with the conformal dimension exactly 1. So this phi hat here is exactly this phi n. So and I write this phi hat. The conformal dimension is phi 1 plus gamma phi hat. So it gives you this denominator. And if I want to expand this denominator, I will find that 1 minus gamma phi will give me some 2 minus gamma phi delta tau when tau goes to 0 plus the normal finite expansion. So this term doesn't matter when my two tails are separated from each other, but when they are coincident, especially because I'm doing the integration, this will really give you something finite. Yes, will give you something finite. And maybe let me write here explicitly with some epsilon or lambda to show it's at the next order. So here you can say there is the order mixing, and the structure constant lambda tt phi is also at order lambda. So maybe let me use epsilon. I'm sorry. So if I combine these two together, I will find I integrate this from minus infinity to plus infinity. By doing so, I just mean I integrate along the whole line defect. And I will get that this part gives me the contribution to lambda t phi hat over gamma phi hat with this epsilon exactly cancel each other. And of course, this BO phi hat because the PE now the double tilt now appear as a phi hat at the moment. And this is the finite part, and I want my integral part to come back. So here I write this as two parts. One is the 1/2 part. This one, because it's this denominator gives you tau 1 minus this, and if you expand it perturbatively, you'll find a 1 over tau here. And this 1 over tau integration from minus infinity to plus infinity will be divergent. And this divergent, if I now do the parameter transformation and turn it into the cross ratio, it will appear around the around 0. So by doing so, I want to separate my integration region into two paths. One is from 0 to 1/2, so that I can remove this pole. And the second part is from 1/2 to 1, and that part is finite and behaves very real. The same thing. But here I want to subtract the divergent piece. And this is the finite expression for my 2. After I consider this, I will say this this 2, equation 2, satisfy perfectly. But this phi n, well, it always appear in the OPE of this two-tilt operator. But here is like I am doing the perturbative expansion, and I get this term. I get its anomalous dimension is like this. But for example, if I am at the strong coupling of n equals to 4 supermils, this delta phi hat will behave totally in a different way. And here I do not say this denominator, and I don't have to worry about the contribution of this term. And in that case, we will say that 2 has to satisfy directly. But at the same time, we will say that this F2C cannot be a constant, because if it's a constant and you look at here, around 0 to 1, you have a pole, and this cannot be integrated to a finite result directly. I mean, it doesn't convergent. It's not convergent in the integration 0, 1. So this is conflict with the claim in some in the papers. I mean, in some literature. So we think the results are probably problematic, and this F2C shouldn't be a constant, at least at the connected order.
So
dimension is variable, right?
What?
So you when you do a conversion, it's on this dimension.
It's dimensionless. Yeah, I agree. But at weak coupling, because we have this perturbative expansion and we need to take this into consideration explicitly, and I will show you like what we can do with these integral identities. So as Nadal promised, this would be a super technical talk. So we have some integral identities. This is cute, but like why it's useful? What can we apply them to? So I want to show it at the in the case of the n equals 12 supermills at weak coupling. So except for these identities, there are some other nice properties. So one is in this paper. They found the first one is what they call the splitting limit, which is when I take this tau 2 approach tau 1, so the cross ratio becomes 0, and I have this F20 is equal to BOJ T hat lambda TT T hat. This T is the rank 2 symmetric traceless tensor. Is because when you have two T hat approach each other, let's say Ti, Tj, it will somehow give you some delta naively. Sorry, this is pinching limit. And the second one is the splitting limit. This one is tau 2 goes to tau 1. And this splitting limit is really when my bulk operator is far away from the defect. So it's x0 perp goes to infinity. So in that case, the bulk operator can barely say the two tilt operator. So it gives me F10 is equal to a OJ CT hat. This is 2. This is 1. And in supermills, there is the so-called topological sector, which is a constant and is known at all the orders of lambda. And because it's a constant, here we can, of course, take the I equals to 0, and we say that this is always equal to F10, this thing minus 2 F20. So it's totally determined by the some very simple combination of the CFT data. So now let's do it. by order. Here, let me write the remove the pause. So at leading order, F1, both F1 and F2 are constants. So F1 chi is equal to BO T cut lambda, and F2 chi is equal to AOJ CT. But remember that what we want is the connected correlator. So F2C, after doing the subtraction, will give me 0 at this order. But F1 is finite. So, if we plug in what it is in that expression, and we will just have the integration of this thing. This is very straightforward to do. And we find that from 1, we get the integration gives pi. So pi o the t hat lambda tt is equal to 3 times 3 minus 1 bo hat. And this thing this is a data that is very easy to get. Why I'm saying so? Because it's from the relation between this and the integrated OT hat. We already know some AB identities. And as long as we can calculate the 1-point function of this O in the bulk, we get what this BOT hat for free. And I actually want to show you that in N equals to 4 supernomial set with coupling, we have this AOJ because they are calculated in all the orders is equal to square root J larger than limit to J over 2 plus 1 IJ So you see this one hold explicitly at all the orders. And once you know this thing, and the defect data is also is easier to get compared to the bulk defect data. So you get this thing immediately without taking the explicit Feynman diagram calculation or any other direct calculation. So in N equals to 4 supernomials, they are all calculated because this is BPS operator. This is, I mean, every operator appearing here are BPS. So they are calculated in all the orders, and we check they satisfy explicitly. But just give me 1 more minute because I will show you the non-BPS defect operator that is not calculated. So from the problematic second identity, we will extract such things. But in other cases, for example, on model where the T hat is not protected, and of course you cannot use this topological sector stuff. This one is also a very straightforward way to get what this the right-hand side is because if I have a bulk defect system, the most straightforward calculation should be the one-point function in the bulk. So this thing, because it's 0, so we say the integration part vanishes directly. What we will have is 2 lambda tt phi hat bo j phi hat is equal to minus j bop. So let's look at this term. This is known from the pure defect calculation. And this is known, as I told you, that you can get it's known at all orders. It's from A, but even at the leading order for arbitrary J, this is not useful. It's just a little, because this phi hat is not protected, it's not that easy to calculate this directly, but anyhow, you can get it directly here. This is the leading order, but I will move to the next leading order immediately. This is at order j over 2. But I just want to emphasize that even if it's at the leading order, this thing is not known in the literature, so I assume it's not that easy to calculate it very straightforwardly for arbitrary J. But phi hat again in n equals 4 superMLs, if I say the Wilson line is coupling to, let's say, A plus I phi, and I mix it to phi 6. So the tilde operator is phi 1 to 5, this 5 scalars, and this phi hat here is phi 6. And as the next leading order, we will find that the F2 or F1 are not constants anymore. The reason is that if I draw the Feynman diagram, this is the diagram for F2. F1 is, you can get F1 from the topological sector. So this is allowed by the planar limit, but even if this is the only Feynman diagram, this is not allowed in the planar limit. So finally, F2 is still a function of the position of these two tails. It's not a constant anymore. But anyhow, we can, this is not a very hard calculation to calculate this Feynman diagram. It's known what F2 is, and we can again plug F2 into these two identities. So because we know the topological factories to all the orders, the reason is that they are all BPS operators, so it's not that hard. And we get F1 and F2. They are all functions of the cross-racial type, and we plug them into these two integration. And this one is easy to check that it holds straightforwardly at order lambda. But here is again as at the leading order case, because this thing is not calculated. So And this integration is not that hard to do, so you can get what this is at the next two leading order directly. And there is some I didn't really do the calculation myself, but I assume it's because it's arbitrary. No?
It's not very hard. Nobody did it.
Yeah, just
You got it for free.
or you can just use it and get it in 1 minute, if not in seconds.
Your formalism is correct. So you said it was, you also need to subtract these poles at some point, so just want to make sure that I did the right thing. You should also check this calculation.
I would say the opposite way. So it's like these things, because you can say it in principle that is correct, is just from the idea of the symmetry breaking. And we can use this to check if the calculations in the literature are correct or not. And in fact, we have found some mistakes.
If F1 and F2 is not constant, how do I solve the equation to get the F1 and F2?
This is a good question. If they are not known, there are some very strong constraints for the bootstrap. You can
Must need to use it.
not really the numerical way. You can also do the analytical bootstrap to fix some.
Okay, any example so far?
The example that we can do, so I don't know any example in this bulk defect case, but if for the pure defect case, I actually know quite a few examples. One is so in the thesis of Gabriel Bliat, he wanted to calculate the 4-point function for 1/2 BPS Wilson length in ABGM theory in 2-loop order, something like that. And there are some prefactors. He called epsilon that he didn't manage to fix, and but with this integral identities, it's very easy to fix this epsilon. And other cases are like in the Devstock. So if you purely use the bootstrap analytical bootstrap method, you, for example, get the 4 tilt. It's equal to a function. I shouldn't use F. J is even worse, but anyhow, as alpha J2, let's say it in this way. And because I know that the integrated 4-point function needs to be 0 from the defect identities. So the integration of J1 gives me 0, but the integration of J2 gives me non-zero. So then you say this alpha, this undetermined alpha has to be 0. Unique solution to this F.
Yes, because initially I assumed that it's constant and should satisfy of course it's one solution. But we prove that it's a unique solution.
I don't think so, because integral is, there are too many things it can appear in the integral. Firstly, I would say you have to combine this with the theory data that you know. It's really the bootstrap method.
Yes,
but there are many theories. All theories will have different correlations.
Yeah, for example, in some ones you have log chi, some ones you have poly log 2 chi. They have different bases.
if I fix a theory, I consider one theory, then whether I can find a unique solution.
How do you think? What does it mean?
If I will give you
If you have a theory, told us you should go and calculate Feynman diagram.
Maybe let me say it in this way. For example, again, I'm looking at n equals to 4 supernomials. At strong coupling now, at leading order, I will assume that my 4-point function have bases log chi and log 1 minus chi. And at the next leading order, I will assume they have log chi square, log square, the mixed ones, and the polylog 2 case. Even at different orders, they have different bases. So it's very hard to say I have a unified solution to what f is. But if I say I have some, let's say, coefficients a1x, a2x, and I will say these integral identities are very helpful to constrain what this a1x and a2x could be, but I cannot find a unique solution unless these bases are really very simple. As you said, they are constants on.
I want to ask a question because this situation is a little similar to solving Swinger's equation. Usually we solve the Swinger's equation by numerical way. We also do not know where is the unique solution. We need to be very clear about whether we have many solvable or not just one solvable. So, but if we have more solution, not just one, this means that we have some non-perturbative effect to this solution. So it's why I said this information. Okay.
Thanks for the question. Okay, I have run out of my time, so let me just give some quick comments. These identities are what I got from if I just integrate one tilde operator. But if I increase the number of the tilde operators when there are contact terms, I will have the equations that are again scheme dependent. But so far I didn't really touch any scheme dependence. So I have to use the technique that Nadav shows in his talk to I will have L2 stuff, and I need to subtract this scheme dependent part and get the pure scheme independent solution. And the formalism is basically the same as in the defect case. So this bulk defect system is a very natural and straightforward generalization of the pure defect case. It's somehow strong evidence to show how universal the formalism that we constructed in that work is. But you say here we can really get many useful data and out of this approach. And also if you are interested in Bootstrap, they are also very useful constraints. Yeah, that's all for my talk today. Thank you.